Hello and welcome to another video. In this video we're going to be working on determine if a cell is reachable at a given time. And so in this problem you're given four integers that are starting points and final points. So you have start x, start y, finish x, finish y, and then non-negative integer t for time. And you have an infinite 2D grid and you want to start at this cell, sx, sy, and at each second you must move to any of the adjacent cells. Return true if you can reach the finish after exactly t seconds, or false otherwise. A cell's adjacent cells are the 8 cells around it that share at least one corner with it. You can visit the same cell multiple times. So in this first example, you start at 2 and 4, so we can draw out the x-axis here. So it'll be like 2, 3, 4, 5, 6, 7, and their y is decreasing. So you have 4, 5, 6, 7. It doesn't really matter like if you're going this way or that way, if this is the same, right? So it doesn't really matter. Okay. And they're basically asked, can you get there in time 6? So they're saying you can, because you would go here, 2, 3, 4, 5, 6. So you can either go straight, like right, or down, or diagonal. And the key to this problem is basically figure out, instead of like, can I make it for this exact time and what's my exact path to this time, instead what you can realize here is what's the fastest way of getting to the finish, right? Like if I start at the start, what's my optimal path? And there's a few optimal paths, but essentially if I can go right or down or diagonally is always better, because diagonally will always get you there faster. So for example, if I go like this, I go 4 diagonally, and then I go 2 here. That's always going to be faster than going less diagonally and picking something else. So let's say I only go 3 diagonally, then now I need 4, 5, 6, 7, and so on, right? So every diagonal path you take, every diagonal step is like 2 steps, right? Because this is the same as right and then down. So diagonally is always optimal. Now, because you can only take 4 steps down diagonally and the rest has to be forward, you can do it at multiple locations, so it doesn't really matter. So this would be one of them. Then you can go like this. These are all equivalent, right? Or you can go like this. But essentially, or you can even go like some stupid stuff like this. You know, as long as you go diagonally for 4 times and the rest of it's horizontal, that's going to be your optimal path. So how long does that take? So let's take a look. So let's just say we just go diagonally straight away. So we have 1, 2, 3, 4, 5. So it takes us 5 seconds. Now the other thing to notice is if we can get there less than 6, right? Like if this takes 5, then anything above that, we can just kind of like go back and forth. Or do some like walking around in a circle, because we're allowed to go back to old cells. So like if we want to get here in 5, and let's say instead of 5 we want to get here in 6, well, instead of going straight here, we can just go somewhere else, like up here, and then we would add 1, right? And if we want to add 2, we can just do something like we're over here, and then we just go back and forth, and then go to the end, and so on. If we want to add 3, we can do this, go back and forth once, then go up here, and so on, right? So like, if let's say we wanted to, so our optimal is 5, let's say we want to get there in 8, we could do like 1, 2, 3, 4, 5, 6, 7, 8, and so on, right? And if you wanted to go like 9, you can go here, 9, and so on. But basically the idea that you have to recognize is if you can get here in the fastest amount of time, you can always just like find some sequence where you just go in circles until you get to the time you need. So essentially the problem comes down to, is the time that they're asking for less than our fastest time to get to the destination, right? Because it's pretty obvious that like if I can get here, obviously if like the fastest time is 5, then 5 plus 2 to the n, where n is any number, would also work, because I can just like go back and forth and add 2 as many times as I want. 5 plus 2 to the n plus 1 will also work, because I can do this back and forth thing, and then add one more step like this. So essentially for any kind of this, basically like this is always going to work, and this is always going to work. So once you recognize that, then you know that, okay, let me just figure out like the fastest path. The fastest path involves going diagonally as much as I can. So I just figure out like, okay, how far diagonally do I go? Plus straight for the rest of it, right? And so let's look at the second problem. So in the second problem, they do kind of already show you the optimal path, where essentially you do go diagonally as much as you can. So you go 1, 2, 3, 4, this is optimal path, right? You can only go diagonally twice here. and they are asking for time equals 3, so this is too slow. So then you can't do it. So just to sum up, for some points, calculate fastest time, then just see if that's less than or equal to t. And if it is, then we can do it. Otherwise, we can't, because we can always stall by just going in circles once we get to the end. So the question is, given some points, right? Given some points, let's call it, let's just get some example points. Like let's say we have our starting x is 1, our starting y is 2, and let's say our end x, final x is 7, and our final y is 5. And I'm gonna draw it, actually to make it, let's make it easier to visualize. So instead of 1 and 2, we'll just make it 0 and 0, just so I can easily draw it. But it's gonna be the same way pretty much. So sx equals 0, and then sy equals 0 as well. Just to make it easier to work with, but this doesn't really matter. Like these points don't really matter. So I'm gonna draw it like a normal xy graph going up, just so we can visualize it easier, but like I said, the starting points and ending points don't really matter. It's gonna be the same way because we're just calculating distance. So if we start at 0, 0, and we are trying to get to 5 and 7, we know that we can get to 5, 5 by going diagonally, right? So we can go diagonally here. So this part is diagonal, but then we need to get to x equals 7. So we're going to go 5 diagonally and then 2 horizontally. So our time here would actually be 7. Right? And let's do a couple more points and maybe we can see a pattern. So let's say we have this exact, or let's actually leave that there. Let's say our points now are, we're going to start at 0, 0 again, because like I said, that part doesn't really matter. Let's say we have 7 and we have 10. And let's figure out like how far we have to go diagonally and then how far we have to go horizontally. So if we have 7 and 10, x is 7, y is 10. So we can get to 7, 7 diagonally. And then we have to go another 3. Right? So we have to go another 3. So this is going to be 7, 3. So our time here would be 10. So notice that basically no matter what happens, the total distance of diagonal plus horizontal really just ends up being the maximum of the two distances of dx and dy. And what I mean by dx and dy is dx. So if we have like starting x, starting y, and then we have final x, final y, dx is the distance between starting x and final x. So dx equals the absolute value of sx minus fx, right? Just the distance. And then dy is the absolute value of starting y minus final y. So no matter what your 2 points are, you just calculate the two distances, and then your time is going to be the bigger one of those. Because if, let's say, dx is 5 and dy is 7, then you can go diagonally for 5, but then you have to go horizontally for the other 2. Similarly, if it was the other way, if it was 7 and 5, you'd have to go diagonally for 5 and then horizontally for the other 2 and so on, right? So you go diagonally up until you hit the minimum of the 2 numbers, and then you have to go horizontally for the rest of it. So basically, your time is just the maximum of dx and dy, right? And we can even look at this. Let's just look at some points on this graph just to make sure we are correct. So let's say we have a point here and a point here maybe, right? And we'll figure out like what's the optimal path and so on. So this point is 2, 6, so let's write that down. So 2, 6, and our end point here is 7, 4, right? So dx here would be 5, and dy equals 2. So according to our formula here, our time should be 5. And let's take a look. So like I said, we go diagonally as much as we can. So we would go 1, 2 diagonally, and then horizontally 3, 4, 5. And so that does work. Let's try maybe one more just so we can convince ourselves. And then we can be done. So let's say we actually delete a lot of this. So we have, yeah, there we go. So we have a little bit cleaner. So it's like 4, 5, 6, 7. Let's say we take point, this starting point, and then maybe like, I don't know. Let's say we even have like this point. Or let's say we do this point. So the x here would be 2, and the y would be 4. And for this point, the x is 5 and the y is 6. So dx is 5 minus 2, so that is 3. And dy, and like I said, you do absolute value, so it's just, it doesn't matter which one you subtract first. Dy is 2. So according to this, our time should be 3, right? The biggest one of these two. So let's take a look. So we are going to go diagonal as far as we can. So 1, 2, and then linear to 3. So this does work out. So that's basically the answer is you just get dx, dy, get the biggest one out of those, and that's your time. And if your time's above that, you can always just like loop around in some way, right? Like let's say you had these 2 points. So you can get here in 3, but let's say I wanted something like 4. So instead of going here, right? So instead of going 1, 2, 3, I can just like go down and then across, right? There's always a way to add 1 second. If I wanted to add 2 seconds, any multiple 2 is very easy. I can just go back and forth like this. And to get any multiple 2, so I could do like 1, 2, 3, 4, 5. You know, if I wanted to add, let's say 3 seconds. So basically the combination of going back and forth and doing this, going one down and then diagonal, will basically let you get any other time. Also, like I said, a diagonal is equivalent to a down and then a forward. So even if you couldn't do this diagonal thing here, at the end it would still work out, because instead of taking one of these diagonals, you can just go down and forward instead to like add 1 second and so on. So there is one edge case that I did not talk about, and I kind of ran into it when I was testing this. And the only edge case that you can't add time for is if your start and finish coordinate is exactly the same. So if your start and finish coordinate is exactly the same, you can't add 1 second to your time, right? Like if your start and finish coordinate is here and time is 1, you can't get here at 1, right? Because you can't go back and forth in 1. But any other time than 1 works. So this is the only edge case that there is if your start and finish is the same and time is 1, then you can't do it. But anything else works. Like if time was 2, you could, because you could just go diagonally or like any direction back. If time was 3, you could do it as well, right? You can go like 1, 2, 3, 4 easily, right? 1, 2, 3, 4, 5 by just doing one, like, you know, combinations of like 1, 2, 3, 4, 5, and so on, right? But this is the only case that you can't, where if your start and finish coordinate is the same and time is 1, because you can't like do a loop in 1 second. That's basically the only edge case of this problem. Other than that, it's pretty straightforward. You just have to recognize that the fastest way is a diagonal, and any other bigger time automatically works because you're allowed to revisit cells, you're allowed to go diagonally. You can always just loop around to add time. Okay, so now we can code it up. So we can say if sx, we'll handle the edge case first, equals fx, and sy equals fy, and time equals 1. This is the only one we can't do, so we will return, I think they want you to return -1 or something, or false. Yeah, I think it's false. So this is the only one that doesn't work when you do the dx dy. Otherwise, the rest of it we can handle with dx dy. So we're going to say dx equals absolute value of start x minus fx, and dy equals absolute value of start y minus fy. And let's return t is greater than or equal to the maximum one of these, right? So the time is going to be the maximum one of these. And let's run it. Let's take a look. Looks like we're good. And yeah, there we go. And as far as obviously, I'm not going to go too far into time complexity because it's basically or how to get like an optimal solution here or whatever, because this is just like whoever makes the least amount of variables, because this is an O of 1 solution, right? So if you like save some variables, you're going to like do a lot better and stuff. So that kind of stuff doesn't matter. And I do think this problem is like, while I don't think it involves too much really math. It's more kind of like intuition, like going diagonally is faster than going down and then across. Once you recognize that, and once you recognize that, once I find like the optimal strategy, how do I calculate it, and then any time above that works, then it's pretty straightforward. So that's going to be all for this one. Hopefully you liked it. If you did, please like the video and subscribe to the channel. and I will see you in the next one. Thanks for watching.